Hello? Can you guys hear me now?
Yes.
Okay,
Yes.
now you can hear me.
Yes.
But did anyone got to be the host now?
Yeah, I think Merate did.
Right. If you can,
Sorry, what did I do?
you are now the host. If you can.
Oh, I didn't know that.
No,
I'm
no,
sorry.
you're host again. You're host again. You show up as host.
I'm host again. Okay.
Yeah.
The thing is, I'm not sure if it's going to interrupt after a while, because I think I should have done login again for a Zoom to understand that this is the long-term recording.
Oh,
Anyway,
no.
this is being recorded in cloud already. So I guess if it stops again, I suppose this will be recorded there, right? So you agree
In
with it?
principle, yeah.
Okay, just so that I will not do any mistake. Did I do something special? Because I didn't
No,
I didn't do
it
anything.
didn't do anything. No, it didn't do anything. It just
I
happened.
think
That
it's fine now. No,
Oh, okay. All right.
Zoom
All right.
just
I
chose
didn't
you.
realize. Okay.
yes. So I was just saying here because there is because of all these technical issues that we have been constantly having. Well, me particularly, not you. But we are about 2 hours and a half below the schedule for what was supposed to be at the moment. So next Thursday, it's still going to be SM1. Perhaps if things go well, we can start with SM2, but I will not assume that we will already start SM2 on Thursday. So it will be still SM1. And I foresee that we will need, so next week on Tuesday, there is a problem because I have a student that is defending his master's degree, and I won't be able to come here. And the place where I will be in Aveiro, in my office, the internet is terrible and there are other people around, so it's not the best conditions to teach there. So it's not going to be easy to do that next week. Well, we can either have something, do it on January. So there are Tuesdays in the afternoon, at least 2 Tuesdays that I would use as like potential blocks to compensate for this for these delays, if all of you agree with that. Of course, there is one more student that is not here, and he will be on the SM2 course. I will talk to him. But guys, would you agree in having, for example, I guess it's on the 4th of as a possibility on the 4th of January afternoon, this same time that we are now, another yes. I don't know if the government will allow it. There is that thing. At the moment, yeah. At the moment, I have all the. Basically, all the schedule is still for that week for MAPFIS, but I think universities have. Yeah, if it's going to be, if I will be at home or not, if that's going to be mandatory or not, that's a different story. But there is this thing. So next Thursday will be SM1 still, and SM2 is only starting next week. One of the suggestions here was to make the first SM2 on a Wednesday, that nobody has lectures, but there are some group seminars and other things, so I'm not sure that that's going to be. It can be in the morning as well. So I might send an email around just to ask what are the possibilities and asking you guys for your preference.
Yeah, maybe a doodle or
a doodle, something like that.
Something
So
like
what
that,
I foresee is that even to make things so that we can cover the topics properly, even in the second course, that we may need 2 extra slots, so of 3 hours. That will be potentially during next year. Well, no more than that, and maybe the second one will be only partially used. That's at least my prediction at the moment. But perhaps a doodle. I will send a doodle around for everyone that is enrolled in these 2 modules, and we will and we will agree on that. Okay, but now with further delay, let's start with today's lecture. So today's lecture 6. Uh, so today is lecture 6. 6. Okay, so today we are going to talk about something that we so last in the previous lecture we looked into Noether theorem, and we studied the conserved what are the conserved charges. Okay, so this is right. What are the conserved charges? And we understood that for continuous global or and even local symmetries, there is a Noether current and a conserved Noether charge, which is where the conserved quantity comes from the fact that you are taking a time derivative. You have this d mu j nu, and you have the time derivative that gives you the conserved charge. So the time derivative is 0, so you have a law, a conservation law, basically. So what, just to put in words, so we have verified this, j mu equal to 0, and we found also that when you have like d0, j0, so this is equal to 0, this gives rise to the conservation, so to this. So q is d3x uh, dq, but this is a different q. This should be a curly, but I will, sorry, not q, like this, d dt, and so dq dt, dq dt. Right.
Kind of related to this.
Yes.
Because last class we saw that there was no gate invariance for the property, for example.
Yes.
But for example, imagine that in real life the the photon had a mass. Then
Yes.
that would mean that the potential, for example, for me the physical field is the electric field, but then the
Yes.
potential would have, we will be able to distinguish between potentials, for example.
What do you mean by distinguishing between potentials?
Because potentials
You mean by
are
the electric?
arbitrary up to a base transformation, so you
Yes.
can't observe potentials in real life, only in the electric field.
Yes.
But if somehow the photon had a mass,
Mm-hmm.
we then the field with physical meaning will be the potential.
Yes, but if the photon had a mass, so everything would be quite different. Well, depending on what is
Depends
this
how
mass,
it's
of
very
course.
small something.
Depending on what is that. If it's very small, it's approximately, it would be approximately the same. But if it had a mass, you could see you could start seeing polarization, longitudinal polarizations as well. So it would not be only these electric and magnetic polarizations that would see. You would also see like a longitudinal one.
Because
That would be kind of the distinction in
I
a
saw
way.
that there's an experiment in quantum mechanics which is called
Hmm.
the Bon, I don't know,
Right?
something like that. That apparently the potential has a physical meaning. They
Yes.
send an electron to different patterns, and the Born Aranov or something like that. I don't know if you know.
No, I'm not aware, but that sounds interesting.
It's an experiment which apparently shows that the potentials have physical meaning, something like that. That will break gauge invariance, in my understanding.
Well, depends. You can still look into the potential, like the electric and or the magnetic field itself, and they have a physical meaning. So
It's the fourth time something.
exactly, uh, but it doesn't mean that there is no gauge invariance in there. So what what is the difference? So if it has a mass, what is the difference that that experiment is trying to? What is the claim of that experiment? If are they claiming that gauge invariance is not fundamental, or what is the?
Perhaps. I'll buy it.
that's the thing that I don't understand immediately what is exactly the claim to understand the goal of that.
This is something that I had on my mind.
That's we can if you can have a look and then you can we can discuss that at a later stage. I'm really not aware of those experiments, but that does indeed seem to be
So
something
during the
interesting.
break, I might look it up on the phone.
Okay, that's good. Okay, so in the previous lecture, so these results that we achieved so were related to it's like internal symmetries. So we studied internal symmetries. Symmetries. Now we are going to study now as a second step. So this were related to internal symmetries. Now we are going to look to space-time symmetries. Space-time symmetries. And when we are talking about space-time symmetries, we are talking about translations or Lorenz transformations. And altogether, that they form the Poincare group. When you have Lorenz, a Lorenz boost, and rotations plus translations, that forms the Poincare group. But we will start with pure. Let's start with pure translations. And for this, if you are doing pure translations, we can represent this in the following manner. So a certain field, psi x, also psi prime x prime, right? This is there is a transformation, a translation in this case. This can be represented as a certain transformation on the field psi x. So we can represent this in this way, where s can be written in an exponential form. This is just an schematic representation. So in terms of a small parent, I will write simply a small s like that, e to the power of s, and you can expand this to 2 small s, 1 plus s plus, so terms of higher order. So this s is a small parameter that you where you can expand and you can and where you can rewrite your field in terms of this. So applying this, you can redo this in the following way. So you have psi prime x prime equal, or approximately, because this is an expansion, so this is not exact, but it's approximate, and that's enough for what we want to do. We want to look into infinitesimal transformations. In fact, s psi x, so this is coming from this here, um, and this is you can now you can now add and subtract. This is now just a thank you. Just a small trick to reorganize your terms. So this is this type of psi. You can sum psi x prime and then subtract psi x prime, and then add what was above, psi x plus s psi x. Of course, just to remind you, this is 0. And this yields, you can isolate. So psi x prime minus, and now we have here inside psi x prime minus psi x plus s psi x, right? And now recall, I will put here just one side calculation. So let's put here. So this is equal to something that we will continue below. So because for now, let's just recall that we have from the definition of the derivative, of derivative, you have d nu psi x is equal to, so this is familiar to everyone, psi x prime minus psi x over dx nu. So that dx is nu, so dx nu. So in this star above, we can write simply the following. So we have psi, so psi x prime minus delta x nu d nu psi x plus s psi x. So in fact, we are talking about translation. So this s is proportional to the identity. So it does not going to do much. And since it's a small parameter, we will be able to ignore it. Let's keep it just for concreteness for a while longer. So now I have this. Now this was equal to this psi x prime, psi prime x prime. So let's recall this is equal to psi prime x prime. So we can write the following. So psi prime x prime minus psi x prime, it's approximately, and this I should put here, this is an only approximately because of the expansion. It's approximately minus delta x nu d nu psi x plus s psi x. Thus we have because we can call this as delta psi. So from here we take that our delta psi it's approximately minus dx nu d nu cx plus s. In fact, I will already say equal to this to first order. No, I will still keep because I will rename things plus s. So x, and now to first order, and making, let's call dx nu equal to a nu. So a nu is just a distance. So this is this is what is basically quantifying our translation. Then we get that the delta psi is equal to minus a nu d nu psi x. So we will now you will see why did we do this, because we will use this result in what follows. So we had seen that we have a conservation law. One of the things that we have verified above if you above, I mean, in the previous lectures, uh, was that the variation of the Lagrangian, so our delta L, which we wrote as sum in I the L the sorry, this is, yeah, there will also be this one, but let's start with this. The psi I delta psi I plus dl, now with the derivatives of the fields, of course, delta dl d mu psi I delta d mu psi I. We have verified that this is equal to 0, and it was from here that we got to the result d mu j mu equal to 0. But now, what we have to do basically is also to consider the derivatives with respect to the space-time coordinates, because now in the previous case it was only for internal symmetries. So for internal symmetries, like transformations in the field space, internal symmetries. It was for internal symmetries. I will write here. It was done for internal symmetries. Transformation, that is transformations in the field space. Now, for space-time symmetries, for space-time transformations, one has to consider the coordinates. The coordinates. And therefore, our delta L, so I will copy this, I'll put this here, like this. In fact, I will need a little bit more space. Let me just put this here and try to compress this a little bit. In fact, so I don't want to sign terms and conditions at this time. Right, so now we add another term here, which is dl dx mu delta x mu, and this is equal to 0. I'll put in green to avoid any confusion. This is equal to 0 because of the invariance of the Lagrangian under space-time transformations. This is why this is equal to 0. As well as before, above, this is 0 because of the invariance of the Lagrangian under internal symmetries transformations. So you have a gauge symmetry or a global symmetry, you transform your theory, and the Lagrangian is invariant, and so we can say this, which gives rise to the conserved currents, the charge density conserved current. Here, in the same way, we are going to have a conservation law, basically a conserved charge, conserved current, which will result from transformations in the field space that leave the theory, in this case the Lagrangian, invariant. And this is what we are going to first do for the space-time transformations. Right. So the very first thing to note is that we can rewrite the green part not only the green part. In fact, we can write a great deal of this in the following way. So let me identify small steps here. So from the Euler-Lagrange equations, exactly here, this is equal to d mu dl d d mu psi I, this part. So this comes from the Euler-Lagrange equations, from Euler-Lagrange equations. We get this, and with this we can write the following, right, for this green part. So let me rewrite the green part in a more convenient way. Right, so we can write this sum in I. So I will drop the sums because we know that there is a summation in I. I will just write it. So I will drop, and further ahead I will put the Einstein convention. For now, I will just say that I'm dropping I will drop the sum in I, but the sum is there. So we can observe the following for this green part. We have then d mu dl d mu psi I delta psi I yeah, plus dl d mu psi I delta d mu psi I plus, and now and I write in blue because now it has to do with this blue part, plus dl dx mu delta x mu, and we can further further do the following. We can also add, and let me put even with another color. Let me choose another one, can be orange. We can even sum plus L d mu dx mu. This d mu dx mu is just this dl dx mu. Noting that this is a constant, this dx mu is a constant. So this, in fact, this bit is 0. This last bit here, it's 0. Because the x mu, which we define as a mu, is a constant. We are considering a constant translation. Constant. So we can reorganize these terms. And you see, this, you can put the derivatives outside and rewrite everything as follows. D mu, and of course, I should say that this is equal to 0. This is equal to 0. Because this is dl, which means that we can write this in the following way: d mu, and now dl d mu psi I delta psi I plus L dx mu. And this is what we have above. So we now have to subtract this minus this orange part, basically. Minus L d mu dx mu, which in fact is 0. This is only for consistency, but this is 0. So this is simply going to be equal to 0. So this is not going to play a role, but it's only written here for consistency because this is the orange part. So I will just highlight this with orange. We have to subtract the orange part so that the original, the starting point is recovered. And we take from here that our conservation law looks, but we will further develop this, something like that. The mu dl d mu psi I delta psi I plus L dx mu equal to 0. Right, so this is our intermediate step before we apply what we have derived above for delta psi and dx mu. Right. So we have seen above that, let's recall here that our delta psi I is equal to minus a nu d nu psi I, and our delta x mu is equal to a mu. So let's replace all of this in the above equation, and we get d mu dl d mu psi I, and now let's replace here minus a nu. I will use a different letter. No, I can use, let me see if there's any conflict in using mu. It's fine, we can use mu, it's fine. A nu, for the naming that I will use further below, because there will be another nu somewhere, so I will use another naming. A alpha, the alpha psi I plus L a mu, here it has to be a mu. This is equal to 0. Let's continue in the next slide. So we get then that d mu, we can now pass the minus sign outside. So this is simply, I will simply copy and paste this. Copy. This, and here it's going to be, so this goes here, and here we are going to have a minus. But of course, I want to also write in terms of alpha. So there is another ingredient, so I will not put such a big, so I do like that. Minus L A alpha, basically delta mu alpha equal to 0. Now we let's also pass now the A alpha to the outside. So it's a constant. We can pass it outside, put it outside of this derivative. So we have d mu dl d mu psi I d alpha psi I minus L delta mu alpha A alpha equal to 0. I will keep A alpha for, of course, this alpha will, A alpha will disappear, but we can keep it for a while longer just for tracking the indices. The next step, what we can do now is to raise, let's raise this alpha, the alpha indices. Basically, I want to raise this alpha here. So we do that. TL d mu psi I. Oops. Okay, d mu psi I. Now to raise, we use the metric d nu g nu alpha psi I minus L. But now I will also apply the metric here because I have to apply the metric everywhere pretty much. L delta. So in fact, raising an index in the delta, it transforms into the metric itself. So we get G mu nu G nu alpha. So it's the same G nu alpha. A alpha equal to 0. We are almost getting to a known result. Now let's put the G nu alpha outside. D mu dl d nu psi I d nu psi I minus L G mu nu A alpha G mu alpha equal to 0. Of course, this is the same. We don't have to write every single step in this regard, but this is simply a nu here with a nu below. But what we take from here is this part that is here inside, and this is the following. So we have a conservation law. So our conservation law which is this d mu dl d mu psi I d nu psi I minus lg mu nu equal to 0, and this is equivalent. This is typically denoted as, this is the t mu nu equal to 0, where we have our t mu nu equal to L, so just rewriting that, the L, the d mu psi I, d nu psi I minus L g mu nu is our stress energy momentum tensor. This is the stress energy momentum tensor. Yeah, so there you go. This is our, or more simply, energy momentum tensor, which this is something that emerges from translations in space-time. And we can identify conserved charges associated to this. So conserved charges, we are talking about the time derivative. So what are the conserved quantities? So
energy and momentum.
exactly, energy and momentum. The conserved charges are the
Yes.
energy density, or Hamiltonian density, and the linear momentum density. But of course, in the same way that we say Lagrangian to Lagrangian density, we can talk about energy and momentum. So the conserved charges are the
And then in this case, it will be the conserved current.
yes, well, the conserved charge is going to be in fact, is in rigor, the conserved charge is the energy, the total energy, and the linear momentum when you integrate in space-time. I will write that.
Yes.
So the conserved charges are the total energy, so the uh, energy and linear momentum. In the following way. So we can define, so our H equal to T00 is the Hamiltonian density. And H is d3x T00, in fact. And of course, then you can just write this in terms of with T00, just to write one, is you just have to take the derivatives with respect to the corresponding indices. So in fact, is the derivative with the Ci dot, where Ci dot is just it's the time derivative, minus L. So this resembles, this resembles as in classical mechanics, like the associated momentum times the coordinate, um, the time derivative of the coordinate minus the Lagrangian, which is like the Lorenz transformation of the the, the Lagrangian, so the Hamiltonian in this case. I mean, the Hamiltonian is the Lorenz transformation of the Lagrangian. Essentially, this is basically in this evident here. Let me just say that C dot I is equal to D0 D0 I D0 psi I. Right, and we also have the linear momentum density. So I can write this curly thing, kappa equal to T0 kappa. And let me say that, of course, here, here above, the conserved thing is like D0 T00 equal to 0. So there is this conserved, this is a constant in time, basically. And of course, you can integrate and do the same for, so when you do dH dt, this is also equal to 0. Just follow the same. So this is a conservation law. So it's a conserved quantity. It's a constant in time. And also the same for linear momentum. So what is this big kappa here? The 0 kappa should be k, not kappa. K. T0k. And this is the linear momentum density. Oh, linear momentum.
And the other components will be the flux the momentum flux density.
You mean like the TIK?
Yeah,
Yes. Those are those. Yeah, exactly. Exactly. Yes. I'm not going into those, but there are several. But the thing is, the conservation law, in terms of constant, in terms of charges, when we're talking about charges, we're talking about the time derivative. So it's always something that has a d0. So it always has this zero component. That's why I'm not talking about those. They are conserved in the four-dimensional, like in Lorenz four-dimensional space point of view. Yes, indeed they are. But in terms of charges, you look to J mu, the current, and you have a vector part and you have a time part, and the time component is the electric charge, let's say. And when you're talking about charges, we're talking about the time component.
It's just like, for example, in the electromagnetism, we have the current for
Yes.
the vector, which the time
Yes.
part is the density. If you integrate
Yes.
everything, okay.
It's conserved. Yes, everything. Yeah, exactly, exactly. Um, and so this once again, so this the momentum are slightly simpler in the sense that this T0, okay, it's easier to calculate this the momentum because this is, there's something going on with the tablet. T0k, this is equal to dl d d0 psi I or psi dot, of course, dk psi I. So there is a gradient here, basically. Sum over all psi's, all fields, minus, it's minus zero, in fact. So minus L G0K, which is equal to zero. This is equal to zero because the matrix, okay, goes from 1 to 3. So the metric is diagonal in Minkowski space. So this is what we have. Right. This was about pure translations, but we also have Lorenz transformations. This is fun. The Lorenz transformations. There will be a little bit more work out of indices, but in fact, this was kind of a challenge because I didn't find the thing solved in any place. So it took me a while when I did this to just to get the things converging with the results in the literature, because there are many indices and things going on. I will try to do a complete demonstration here. But let's now focus on the case of pure Lorenz transformations now. Pure Lorenz transformations. And this is the last step before symmetry breaking. Right, so there are a few considerations that we need to take into account before that. We have a Lorenz transformation lambda that we can write in an exponential form as for any of this type of transformation symmetries. Let's say this when you have these invariance groups and so on, we can always write them in form of an exponential to a certain parameter that I will call omega. And once again, we just do this the expansion 1 plus omega plus something that is going to be proportional to omega squared. So this is higher order terms. We're never going to use them. So transformation of a coordinate, as we have seen in the very beginning of this module. So we have x prime mu, which transforms as lambda mu nu x nu. And now let's use the transformation property above. So this is equal to a delta mu nu. So this basically this identity is delta, and then we have omega with the same indices as lambda, of course, omega mu nu. And let's just stop here. Of course, we can have plus something like O omega mu alpha of nu, but this is higher order. We will not consider this x nu. And this is simple. We will call all of this as x mu plus delta x mu, where our delta x mu, we should understand our delta, not here, I'll write it down here. Our delta x mu equal to omega mu nu x nu. Of course, this is once again not exact, so this is approximate to first order. So to first order. Right. And let's use also a result that we derived in the first lecture, which was the invariance of the metric under Lorenz transformations. If you recall, we had this result saying that a certain Minkowski metric, so GAB alpha beta, is equal to G mu nu lambda mu alpha lambda nu beta. And we can apply this because we are going to find a crucial property about this omega.
Just one question. The things you're doing here, like in this translation, in this Lorentz transformation,
Yes.
can't be coordinate transformations, right? Because otherwise it's trivial that all theories are coordinate invariant.
What do you mean it cannot be coordinate transformation? So we do a translation?
So couldn't this be the so-called active transformations? We move the points themselves and not the coordinates.
I see this as a coordinate transformation.
But that every theory in physics is, well, as all the possible symmetries.
Right, but there is because there is this invariance under such coordinate transformations, this yields the conservation. This is what we are deriving here is a consequence of that thing that we know that we just said. You said so. All theories in physics have this property of being invariant under coordinate transformations. Yes, that's true. What's the consequence then? There are things that are conserved.
Okay, very good.
That's we are departing from that fact to get to the laws that emerge from there. That's the point. And you can transform coordinates in several ways. You can make pick up the coordinates and just do a translation. So you need to, if you describe everything.
What I showed you, I pick up the map and I.
Yeah, you just move it to another place, and then of course the coordinates of your system will change according to the translation, which is a quite easy transformation. It's but you can also do Lorentz boosts in the same way that we are used to do. So this is really coordinate transformations. And this coordinate transformation, I mean Lorentz transformations and this translation, this act, and in case of the Lorentz, that's the key point. They act on the coordinates, but they also act on the space-time indices of the fields itself, which is not the case for scalars. So for scalars, the Lorentz part doesn't hold, but for fermions and vectors, but we will concentrate on the case of fermions, they hold because the spin is a space-time symmetry. So when you transform when you do a Lorentz transformation, you are transforming not only the coordinate system, but also the spinor itself.
Yeah.
And both things need to go together. Exactly. Right. So So was an important discussion, of course. So let's then take our expansion of the lambda, so the Lorenz transformations, to rewrite this g alpha beta is going to be equal to g mu nu, and now the first lambda it's going to be given by delta mu alpha plus omega mu alpha, and the second is going to be delta nu beta plus omega nu beta. And this is equal to, now let's apply g to the first one. So this is going to be uh, g alpha nu plus, now we lower the index, omega nu alpha, g alpha nu alpha, that's correct. And here delta nu beta plus omega nu beta, right? And now I will multiply these two. So first, acting it on the metric. Um, so the first one, this on this here, gives me a g alpha beta. Now on the second omega plus omega alpha beta, plus now this omega and this acting on this delta gives me omega beta alpha plus a term that is of higher order, essentially. Since we are working on a to first order, so these higher order terms, if we wanted to include them to this calculation, we also had to have expanded the lambda to second order, because there are terms that are not present in this product that would play a role here. So what we do here is just we forget about these ones here. And two lowest order, I mean first order, lowest order would be zeroth order. To first order, we get g alpha, we get that g alpha beta is equal to g alpha beta plus omega alpha beta plus omega beta alpha, from where we take that omega alpha beta has to be equal to minus omega beta alpha. So omega is antisymmetric. Right. So this was just to show the anti-symmetry property of omega. Right, now that we are talking about Lorenz transformations, let's revisit the previous procedure that we did for the translations, but redo this in terms of Lorenz transformations, and recalling that Lorenz transformations also act on the field space. So we will have to consider contributions for coordinates and for field transformations. That S that we ignored previously because this was only identity for a scalar quantity, and for, I mean, for a translation it's proportional to identity, we could ignore because it would not do much. Now we cannot ignore that small s, so we will have to consider it now. So the transformation of the field, and I will put also this Lorenz indices on the psi's now. So first, what we had before, so we had above we had that we had the following. So delta psi was approximately minus a mu d mu psi x plus s psi x. I will also put now here some already some Lorenz indices. I will call this R. I'm putting in color S and here S. But what's happening is this, and I also have to do this. Here we also have a delta. So this is proportional to the identity, of course. Delta S R. And here, in fact, because this is delta, I prefer to put the all indices low down. R S and S R S, and that's it. So we had, this is what we had above. This S was also proportional to identity. Yes, so this was also proportional to delta. What we have now is this omega. So this a mu, which was the translation parameter, now it will be recast in terms of omega of this Lorenz transformation on the space-time coordinates. So now we have, well, we recast it to, so delta psi r equal to minus omega mu nu x nu. In fact, we have this x nu d mu psi s psi s delta r s plus s r s. So I'm putting the s index as this curly x, curly s psi s. I'm just dropping the argument, the x argument now. Right, but there is something that you, okay, let's lower the indices now. In fact, we can just very simply flip this mu and mu. So we'll raise one, lower the other one without just putting the full metric thing here. But we can recast it as delta psi r equal to minus omega alpha nu x nu d alpha psi s delta r s. So this, the r and s are I should write it down here. I will write it down for confusion. S r s psi s. So two notes. First, Greek indices space-time act on space-time coordinates, or as space-time coordinates indices. Space-time. Latin indices. Latin. This is, in this case are spin or specialized for spinor indices. And there is something also that we verify. You see, this omega is antisymmetric, right? Yes, we have just shown that above here. This is antisymmetric. It's on the screen. So we have this antisymmetric. So this is antisymmetric. But here, this is symmetric in mu and alpha. So this product would be zero. So we ought to do something about it. And what we do is just we will symmetrize this product by anti-symmetrizing the mu and alpha ones in the following way. So we do this, and I just I will just say here, recall here that the rule is that when we do this, new alpha, for example, uh, I will not write T, you may think it's the stress energy tensor. So some tensor, ij, not lambda, okay, ij, when we have this anti-symmetrization, this is equal to 1/2. We will keep this. We are not going to expand all of this. We only expand at the end to keep minimal our calculation here. But this is equal to 1/2 a ij minus a ji. So if a, and a stands for anti-symmetric, if you do this, you are clearly now allowing it to be a symmetric product, and it's no longer vanishing. Right. So far so good. What is this S? Now let's write down the S. So for now it's going to be given. I will tell you that SRS is equal to minus I. Some references don't use the I, or it's the over 2, it's everywhere as I found, but some references don't use this I. Alpha beta, S alpha beta, R S. And this is something that is coming from the transformations of the spinors, where the first S, this is a small s here. This is a small s. So this is coming from the transformation on the spinors, where we have like psi r x goes to psi prime r x prime, which is equal to first order. This is simply delta r s psi s x minus I over 2 omega mu nu s mu r s psi s x, where with s r s alpha beta or mu equal 1 over 2 sigma mu nu. You already heard about the sigma mu nu, rs, which is equal to I over 4 gamma mu. Gamma nu, let me also put the indices here because this is rs. It is coming from the contraction of the indices. So the gammas, these gammas are matrices, so they have two indices, each of the gamma mu's. This is something you will use these things.
Capital S, right?
Yeah, this is capital S. It's a little bit hard to write by hand, and there are deltas here. So guys, please don't confuse. This is a delta here. This is a capital S here, as well as here it's a capital S, not a delta. And this is a small s. It's a bit, I'm trying my best to make the letters not confusing, but this is, I hope you understand my letter here. So one of the exercises that I will ask you to do, I hope to put it still today, if not today, tomorrow, and you will end in till the end of next week. And if you need some more time, contact me again. If you have some other responsibilities, if you think you need more time, I can give you one more weekend as for this time.
So there's going to be another.
Yes, there will be 3. In fact, there will be another one, and then there will be even another one. So 3 for standard model 1.
Okay.
Sorry? Yeah, yes. But the exam is also going to be, the exam will be one extra sheet of exercises, but for all the topics. I would like also to talk with you about uh, when do you prefer to do the exams. One of the things would be at the end of the two courses, doing first one exam and then the other one, because you can study the thing in revise the thing in
So
like remembering this one.
the deadline for this next exercise sheet is next week.
Yes, next week, but let me recall
Next
that
week,
all deadlines are
like
soft deadlines here.
okay, but more or less.
It's more or less the end of next week.
The end of the next week.
The end of next
Friday
week. Yes, it's going to be. It will never be. I will always give at least 1 week from the minute I post it on my webpage, and of course I will send you an email saying, "Look, it's online," because I have to solve the exercises before giving it to you, and I want to make sure that I don't solve everything. So maybe if you find something, you can tell me, but I try to solve part of it at least. But one of the exercises, and that I didn't solve, but it's in textbooks, is to show the invariance of this psi bar, the Lorenz invariance. And there, for that, these omegas will show up and all these relations. You will have to read in textbooks, and we'll find out these relations here. So this will be less of a God-given thing. Right now, at this moment, this S transformation is God-given in this course. I try to do everything consistent and following something that we have already derived, but I don't have time for everything. So part of the things that I don't have time, it's for you to do as exercises in the previous one for the chiral representations and so on. Right. So with this in mind, we can rewrite. Let's rewrite our. So okay, we have here already our delta psi r, which is already in the form that is convenient. Let me just check that. Yes, new alpha. Right. Yeah. And now we need to look into the transformation of the coordinates itself. So this one is in the right form. Yeah, this is the convenient the best way. Yes. Now, delta x nu was also somewhere here. Let me go back. Delta x mu, there you go. So it's here. I will just copy this. So copy. All right. So I will paste it here. So delta x mu. Now we can lower the indices. Omega alpha nu, x nu, and now multiply by the metric alpha mu, or mu alpha. Once again, there is like a symmetrization needed here because this product is symmetric. So mu and nu, so we need to anti-symmetrize here to make this product non-vanishing. And this is what we are going to use in our for dx mu. So we are going to use this. Let me put here a dot, and we are also going to use. I will copy from here. I'm going to use this so that both stay side by side. So we are going to use these two in our expansion of the Lagrangian that we not the Lagrangian, but this. So the procedure now is again from the fact that doing this the coordinate transformation, we are going to have that delta L. So this that is here in the screen, the variation of the Lagrangian is going to be 0 under these coordinate transformations. We are going to repeat the exact same procedure that we did for translations, but now for rotations. For yes, Lorenz boots and rotations, of course. So let's do that. So I will drop summation again. So what we had above was that dl d d mu psi I delta psi I plus L delta x mu. This is our starting point, and this is equal to, now we are going to develop this. This is equal to delta. Now let's replace delta psi I. So we are going to replace delta psi I by delta psi I, and we are going to replace delta x mu here by this delta x mu there. Great. So we get the following. Delta L, and now we need to take also into consideration the indices, the spinor indices. D mu psi R okay, psi R. Now minus omega alpha nu x nu d alpha psi s delta rs plus exactly. So I'm separating the entire plus L. You will understand why I'm separating this way, L. And now let's use already the omega. So far we have used this part here. So this part here. I'm now going to use this, and we still have to put this here. So I'm separating the space time coordinates first, and the transformation on the field indices, the spinors, basically at the end of this expansion. So L omega alpha nu x nu g nu alpha. So anti-symmetrization here. And now let's use the S. S is here is this I minus I over 2 omega alpha beta. So minus I over 2 dl d d mu psi r omega alpha beta s rs alpha beta. Sorry, I should use, because I don't want to get confused with the index labels here, because they will change at the end. So to be consistent, because I want the same names here, it's new alpha. Yes, new alpha is the best. New alpha as well. Psi s. Right. And this is equal to. So let's now put omega new alpha outside. Or group, actually, let's group and use the anti-symmetry of, so using anti-symmetry of omega nu alpha, we can write the following. Omega, which omega? It's this one here. This is new alpha. Because I want, here I have alpha nu, you see, alpha nu, and I was writing with alpha beta. In the sum, it would be okay here, because this and this is indices are dummy. But then I want to look into this expression and identify the same objects. So it's just for a matter of consistency. In fact, I will put in, this is not in the current lectures, the notes that told you, this is not, this is very poorly done there. It was something done in a rush. I will update with this calculation there as well. Right, so now we can group everything here. dl, d mu psi r, x nu d alpha psi s delta rs minus L x nu g mu alpha minus I over 2 dl mu psi r. This is an r s nu alpha rs psi s omega nu alpha. So you see what's happening here. So the minus sign. So here now I have omega nu alpha outside because I changed this here. This is equal to minus omega nu alpha. I mean, if there is a minus there, I should just say that this here is equal to that. And that's what I've done here, essentially. And also here. So this. What's happening?
So at the end, you have omega
Here, I mean, here it's new alpha. Yes. It's new alpha. I'm putting outside new alpha. Right. Now, let's group this, group it in even in a more convenient way. Like we are now going to put the x mu. Now, you see now that you have this x nu and x nu that you can put outside of these first two terms. And there will be something emerging from doing so. So if you do x nu, and now dl, it's a bit, I will put like that. dl, this doesn't look now. dl, d mu psi r, d alpha psi s delta rs minus L g mu alpha. All of this I multiply by omega nu alpha minus I over 2 dl d mu psi r s nu alpha rs psi s omega nu alpha. Can you identify anything here at all? Let me paste for a moment a result here. Let me go up. Yeah, exactly. But since maybe not everybody has immediately seen that, I will just copy and paste for at least for a moment this T mu expression there. For everyone to see. So we have derived this stress energy momentum tensor above. And now I will paste it here just for, I will of course erase this. I only want you to see. So you see the similarities here. So what we have here, in fact, as Ilaria immediately said, is T mu alpha. This is what we have. Right, so now I can erase this. I guess this is clear for everyone. So let me erase. No, actually, I can keep it. I can keep it. I think it's not confusing. It helps visualizing. So what we have at last is x nu t mu alpha omega nu alpha minus the other one. Essentially, I will just here, yes, of course, I'm going to copy and paste. Minus this. And the conservation law. So we started from this variation of the Lagrangian. So the conserved, and of course, now let me expand this in the way that it should be expanded. So this is equal, at last, this is equal to x nu t mu alpha minus x alpha t mu nu. And because of this factor of 1/2 arising from this symmetrization, this factor of 1/2 here, right? We are going to remove the two, the two that is here. So we get this. Copy. Minus I. And omega nu alpha, right? And the conservation law, essentially the conserved Noether current will be d mu applied to this equal to 0. And we have two ingredients here. The first one, this one here, we call, and we can just call this in general as d mu m mu nu alpha equal to 0. Where this m is like the angular momentum, the generalized angular momentum current. And this is split in two parts. There is a first part where we can call, so we can say that m mu nu alpha is equal to L mu nu alpha plus S mu nu alpha, where L mu nu alpha, which is equal to this first part here, is the orbital angular momentum current density. Current density, and at last S mu nu alpha equal to this part Oh, what am I doing? There's a hanging index here. There is a mu here coming from somewhere. I don't know. Right, but this part, I can copy this. And this is the, you may guess already, this is the spin current density. Current density. So if I ask you, or if you see a question, so you have a certain Lagrangian, calculate or express in terms of the fields the conserved charges. So the conserved charges of a certain Lagrangian, you have like J0, which is like the equivalent to electric charge. So this has to do with internal symmetry. So it is the charge density. You have like T00, which is the energy density, which is also conserved charge. You have P kappa. This is the linear momentum density charge. You have L0 nu alpha and S0 nu alpha, which are here above angular momentum current density charge, or angular momentum charge density and spin charge density with the zero there, of course. Um, and of course there is an interesting paper that I will cite in the new version of the notes, where they go also to, so you can see there is a paper in a European Physics Journal C. Let me put C, European, it's like that, European Physics Journal C 2018, and the reference 78. This is not in archive, I guess. But this is published in this. It was in 2018, and they discuss this. For example, they say that there is also this current, which is when you have m equal to 0 and nu also equal to 0, because you can have two zeros here in L and S. Mu and alpha can be equal to 0. What cannot be equal to 0 is nu and alpha. Both 0, it just vanishes. But the other two can, and that's also conserved quantity. And from what is written there, they say like a relativistic center of mass with spin. So they just elaborate on this. I think that paper is like an academic exercise, but I think it's quite interesting. And in fact, I didn't know that before I checked that. I asked myself, what about this current? Because I never thought about this extra current. I'm talking about. Let me write here. I'm talking about M0 alpha, if I'm not wrong, alpha 0. I guess this one is possible. 0, so new 0 alpha, exactly, precisely. So you get to something like if you look, if you, in this particular case here, it would be something x nu t 0 minus x0 t t0 nu, which would be equal to x nu, and now here it's the Hamiltonian, let's say Hamiltonian density minus t p nu. So this is quite interesting, and this leads to the the conservation of the, with some arrangement of these things, it leads to the conservation of the center of relativistic center of mass. I'm not going to elaborate on that, but this is a quite interesting thing. You can check in this paper that I have pointed out here, which I find quite interesting. Right. So this is we are going to make a break. We'll start with symmetry breaking after this, but let me just mention that, for example, if you do for this, even for this m m0 ij, where I and j, let me put even 1 and 2, this is equal to L0, 1, 2 plus S0, 1, 2, which is equal to T0, 0, 1 x2 minus T0, 2 x1, okay, plus S0, 1, 2. And the interesting thing here is that this here is P1, this here is P2, and this is angular momentum, the Z component of angular momentum. So this is like LZ, and this gives rise to SZ. So this is the total angular momentum, JZ, basically. And there is it's a conserved, of course, a conserved charge of the theory. Okay, so I propose a break of 10 minutes. And today I think we are on time for us to go to the start with the symmetry breaking and the preliminaries of the Higgs mechanism right after this 10 minutes break.
I understand the question, but it's kind of complicated. Could I draw on the board?
Yes, of course you can. But I just have to go to the bathroom, and then we. I will just pause this the recording. Ok, já está a gravar. Vamos. It's recording. Let's start. So let's change topic now. Let's change topic and let's start with my pen is here with symmetry breaking. I will even write this now with these big letters. So symmetry breaking. Right, we have about an hour to the first to talk a little bit about this. So now we are going, after all this, I know that this all this derivation with of the energy momentum tensor is quite heavy. It's something that tires off a little bit because you need to pay a lot of attention to indices. I can say myself, it took me a while to get this in a neat way because I look into all my textbooks and my notes when I did my QFT course, which was when I learned that bit, and it was by far not a complete derivation. So I had to and then in between there were a few things that were not working in terms of signs and so on. So I understand that's a bit tiring, but let's now try to focus again on this the next step, which is the symmetry breaking, which is going to be a little bit less heavy in terms of notation, I guess. So, and we are going to look into a pure scalar theory again. So, a pure scalar theory, and I guess you know, you are aware of the Klein-Gordon Lagrangian that we have discussed before, d mu phi dagger, d mu phi minus a certain potential, phi star phi, right? Where this potential, and now the potential is going to be the star. Up to now, we didn't say much about the potential, but now this potential is going to be the star of the company. So this V phi conjugated phi is the one that we have introduced before, lambda over 4 phi conjugated phi. So there is nothing new here for you so far, plus this mu squared. Well, this mu squared is the second star of the company, let's say, and lambda is the third star of the company. And phi conjugated phi. Right. This is a theory that has, you may already guess, a U1 global invariance. Actually, we started with this theory to derive the to look into the Noether theorem. We started with this. Right. Now, what is this? Let's recall. What is this U1 global invariance? So this is such that we have our Lagrangian, of course. So our Lagrangian phi. I will just write phi because the conjugated is just conjugating, and this is equal to L. Let's go L prime phi e to the I alpha, where e to the I alpha is just the global. So alpha is just the global phase. We can put here a global charge also, but let's keep it normalized to 1. And we are defining this phi. This is a complex, so phi, and also this is a complex field. So that's why there is this phase, this rhythm of rotating. This is clearly for the reason of it being complex. So when you're talking about charged fields, we are talking about U1 phi charge in terms of electric charge. It's because there is some complex phase that allows for this sort of invariance. So this phi can be recast in terms of, so this is 1 over square root 2 phi 1 plus I phi 2. Now let's study the shape of the potential of this V phi potential. We have 4 possibilities. Let's study all possibilities. It's solved. Possibilities for the signs of the parameters lambda and mu squared. And note that mu squared, so here the squared on mu is just to denote that this is a squared mass parameter. That's why we write squared. But the parameter itself is mu squared. It's not mu. The parameter of the theory is mu squared. It's a squared mass parameter. So, and what are the possibilities then? So, A, we can have lambda positive and mu squared also positive. B, we can have lambda positive and mu squared negative. C, lambda negative and mu squared positive. And finally, lambda negative and mu squared also negative. So you can imagine that for a more complicated potential, if you have more fields, these 4 conditions will no longer be only 4. Of course, this will be a lot more possibilities.
Can the mass become imaginary?
Yes, the mass. No, actually, no. Let's
It gets summed up all the contributions, it doesn't.
That's exactly what we are going to answer, because the mass is not mu squared. This is okay. Mu squared is the mass of this phi, this complex phi. But that's not the physical mass of the components of phi, which we need to minimize. So previously I said, okay, let's not have any consideration about the fields. But now we are going to have strict considerations about the fields. But let's visualize what happens to essentially to the potential in each of these scenarios. Actually, I think to visualize that, it's important to first look into the minimization conditions of this potential. We want to find I mean, not minimization, extremization conditions. We want to find the extreme of this potential and analyze each one of them for each of these four cases. So what is the first thing that we do when we want to be in an extreme, either a maximum or a minimum or even a saddle point? Exactly. We take the first derivatives. So the first step, and this is always what you do when you build a theory and you want to study what are the symmetry patterns, the symmetry breaking patterns, and the masses, the mass spectrum of the theory. The first thing is studying the scalar potential. So to study the scalar potential, first we need to see the extremization conditions or stationarity equations. So first one, stationarity conditions. And the stationarity conditions, there are only two because we only have two fields, two real fields. Let's expand. We are expanding the complex field in terms of its real components. So phi1 and phi2. And we are going to have, so dv, the phi1 equals to mu squared phi1 squared. So basically I'm taking the derivative of, I'm expanding the potential, this potential here in terms of this of phi1 plus phi2 in terms of real fields. And even before doing this, let me just write down the expansion here. In fact, so just to say that the operator phi star phi, this is equal to 1 over 2 phi1 squared plus phi2 squared. This is just the modulus. So this is just the modulus squared. So it's just the squares of each of the real and imaginary parts. Go away. Now, when we square this for the quartic term, the lambda 1, we just have to, it's trivial, just have to square this, and it's 1 over 4 phi1 square, phi1 to the fourth plus phi2 to the fourth, and of course it's a real field, so plus 2 phi1 squared phi2 squared. And it is on this ground that we take the derivatives with respect to phi1 and phi2 to get these conditions. So we have mu squared phi1 phi1, in fact, because it's the mu term. So it's coming from this expansion here, the mu. So we take one derivative. We have 2 canceling these 2, so it gets linear in phi1. Phi1 plus 1 over 4 lambda phi1 cubed. This is already in the lambda term, plus 1 over 4 lambda phi1 phi2 squared. And of course we have derivatives with respect to the second one, which is just flipping 2 with 1. Mu squared phi2 plus 1 over 4 lambda phi 2 to the cube plus 1 over 4 lambda phi 2 phi 1 squared. And this is a stationarity condition, so we need to require that each of these conditions is 0. And this yields, there are two possibilities. For it to be 0, so look at the both up and above and below. If phi 1 is 0 and phi 2 is 0, this holds. One of the conditions, let me put a red condition, is phi 1 equal to phi 2 equal to 0. This is one, there is one extremum here, and whether it's a maximum, minimum, saddle point, or whatever, it will depend on the signs of lambda and mu. Or we have another possibility is if we replace mu squared, you check this, mu squared equal to minus 1 over 4, 1 over 4 lambda, phi 1 squared plus phi 2 squared. Right, so you agree with this one? So, for example, see, mu, it depends in this case on the, but one of the things that this phi 1 and phi 2, they are classical fields so far. So this will be, I'm starting with this because I'm making this generic. But then this phi 1 squared plus phi 2 squared, because we have a U1 phase, an invariance over a U1 phase, you can write, for example, phi 1 equal to a certain V cos alpha, and phi 2 equal to the same V. This is like a radius, so a field value, sine alpha, which makes mu squared equal to minus 1 over 4 lambda V. This V typically is what, sorry, V squared. This V is what is typically called the vacuum expectation value. I was about to introduce it after, a little further below. But yeah, this is, you can already kind of write down this way. Because we have this phase, so we can write, we have the freedom to redefine the fields in polar coordinates. Basically, we have this polar or this rotation, this phase rotation, so we can do this. Okay, now let me put some picture here. I have grabbed the picture yesterday. Yeah, exactly. Is it visible enough? So okay, can be like this. Right. Okay, so we have here already written, so the A, B, C, and D conditions. So this A, B, C, and D. So those four conditions that we have discussed above. Right. If we go to condition A, so lambda and mu square are both positive, then this means that the potential will grow to positive. At infinity, the potential will continuously grow because lambda, so the quartic term which will dominate in infinity, makes it going to increasingly positive values. So the stationary point that we have is this phi 1 equal to phi 2 equal to 0, which is like this minimum. So which is here in the basically in the 0, 0 position. So this is a solution that holds here, and the potential is stable. There is a particle that is sitting in this minimum is stable. It will not try to fall into another deeper minimum because it doesn't exist. So this is a stable solution. Now I will go to C. Of course, I'm leaving B to the last. I'm going to see if lambda is smaller than 0 and mu is bigger than 0. What happens is that for small field values, we have the same behavior as in the case A. But as the field grows to larger values, the quartic terms, which are now negative, will dominate and will push the potential down to minus infinity. So what happens is that we have again a solution here in at phi equal to, so we have a stable minimum here, not stable, sorry, metastable or unstable, depending on the lifetime of this minimum. That's another story. You can have quantum tunneling, you can have thermal jumps, you can have, depending on the problem that you are looking for. But at 0, 0, this red is red always stands for this 0, 0 position. But we also have here like a maximum around. So you kind of see that even in any of these pictures, there is always this rotation invariance. You can rotate via a certain phase, and each of these potentials will never change its shape. So this is the visualization, the visual representation of this U1 symmetry. You can clearly see the U1 here in these potentials. Rotate it, take the Z-axis and rotate it around. It's always the same. Any of them, even with the broken symmetries, it's still, there is still this phase of the full potential itself. I will come to that in a moment. But this is a situation where the potential is called UFB, which means unbounded from below. UFB means unbounded from below. This is a very common wording in any particle physics paper that contains containing any potential. You always have to make sure where are the places where your potential is not unbounded from below. And also, you need to make sure that the minimum is stable, or at least metastable. A metastable solution is not the wrong solution, as long as the lifetime of such a local minimum is larger than the lifetime of the universe. That's a condition for a viable, not in the particle physics context. But particle physics, I mean, that is the context of yeah, that may be a different side. But in the particle physics context, I mean, if we are sitting in a metastable minimum, which with the current mass of the top and of the Higgs, that's
we can dive in the next quadrant.
exactly it can start happening now. You'll start seeing telescopes will start seeing through the universe a different phase. So domain walls, and well, domain walls is when you have like discrete symmetries, but you can start seeing other phases showing up, and you can suddenly we cannot hold together because I don't know, maybe photon gets a mass, or W's stop having a mass, and then the weak force starts being completely different. The sun starts shining. So all sorts of things can happen depending on the phase that you
I
are.
actually read a paper where they said we could survive
A phase transition.
For example, the photon gained 10
Mass.
to the minus 4 electron volt mass.
Mhm.
The only thing that would change would be radio communications, which wouldn't work.
Yeah, they will take ages to to reach. Of course, you would be blind to the deeper edges of the universe, of course, and radio communications, of course.
As for the rest, life could go on as usual.
Like back into ice ages and something like that,
Back to cable, basically.
or to cable, yes. Yeah, exactly, because you need to transport information via an electric current and not like a electromagnetic wave. Yes. Yeah, exactly. That's quite interesting. So, but this potential C is also not desirable. It's not wrong. You can have a model. Okay, I think Etevaldo, it was Etevaldo, right? I think he's back. Great. So I was saying that this C is not like the optimal case. If you build a model that ends up in a situation like this, referees will not like it. But it's not immediately wrong as long as this minimum is stable enough. But of course, this is not what we aim at. Then there is D, where both lambda and mu are negative. This is like the worst. This is UFB, embodied from below. It's unstable also. It's so this red one here in the previous one, it can be unstable, unstable, or metastable. But this one here, again, this is the solution. Um, Again, this is the solution phi1, phi1 equal to phi2 equal to 0. It's clearly unstable. So this D is like the worst case. This is really bad, this potential. Back in C again, here, if you are sitting, let me put a dot here in this maximum. Of course, this is bad in the sense that you can fall either to the minimum of zero mass. I mean, the minimum, the symmetric minimum, where you have phi1 and phi2 equal to 0. So you can fall either in this direction, and that would be okay, but you can fall in this way, and that would be bad. So the mass of this particle here is going to be a negative squared mass. We are going to see that. But here, in this, although you have this U1 phase rotation invariance in all of these four possibilities, for example, if you are here in this place that I'm pointing out, here in this particular place, this symmetry is broken. Not broken in a nice way, because you are not in a minimum, it's not stable, but it's broken because now there is like this there is a certain there's a certain radius which is v, okay, but there is in this very specific place, if you rotate the potential, you change the position of this particle, right? When you rotate, you go to a different place, so you no longer have the symmetry here, but you do have here in the minimum, you do have. And the potential itself, the wall potential, has the symmetry. But if you are sitting here or sitting there or sitting there or sitting there, to go from one place to the other, it's not the same field values. So the symmetry is no longer there. And now the most interesting case, B, where lambda is positive and mu is negative. So this gives rise to this type of potentials. So where you have here a maximum that is, of course, unstable, but you have a valley here, basically all around here. This is a value of equivalent. This is the vacuum of the theory, so it's your minimum. And here, this is similar to what I was saying. You're sitting here in a certain place. The solution is this one here, mu squared equals to -1/4 lambda v. This is what's happening there. Because you have, so your field values are going to be this v. You can write them in that in polar coordinates, let's say. And here, there is no longer only in the minimum, not the full potential. The full potential preserves the symmetry, but only in the minimum, you no longer have the symmetry. In the minimum, the symmetry is lost. This is the feature, because you are here, you rotate the potential, and you go to a different place. This is a bit similar to what we were discussing during the break, in other terms. But I think you understand that in the red dots, any of the red dots here, if you rotate, you're still in the same place. So there is invariance. But in this minimum or this maximum here, So in these places, if you rotate, you change your position. So this is where symmetries are broken. And the breaking is proportional to the distance to the origin, essentially. So the field value, in a way. So you see, this v squared is quantifying you, of course, lambda as well. If lambda is zero, then you lose this. But let's assume lambda is order one, then the value of v, the value of the fields in this minimum will quantify you the size of this breaking, basically, and the scale of the theory, essentially. Because there are two different stories here. You can imagine now that you live, you have two oscillations that you can consider here: radial and angular oscillations. In the red dots, for example, these two, let's only consider the ones where we have minimum. Whatever you oscillate your field, it oscillates always in the same way. But here, in the radial direction, it does have a harmonic oscillator-like oscillation, but in the angular direction, there is no oscillation of this sort. It's a massless oscillation, let's say. If you remove the mass from your harmonic oscillator, it becomes like a flat behavior. Like it's no longer an harmonic oscillator. You no longer have such a solution. So in fact, the mass is associated to these harmonic oscillator solutions around the minimum. So these oscillations I'm talking about are indeed quantum fluctuations. We are going to quantify them here. So once again, radial oscillations, they will have a mass associated to the energy that you need to spend to go up the walls of the potential. But angular ones, they don't cost any energy. You don't change energy by doing any fluctuation, any quantum fluctuation in the angular direction. So once again, I hope this is so this is the second way. So I told you two different ways of checking why the symmetry is broken. The first way was just looking that you are in different places here. But the one that is, and I wanted to say this in second place because it's the one that I find more elegant, is that here the oscillations, they depend whether you are talking about radial components or angular components. It's not the same. Whereas in a symmetric minimum, it doesn't matter whether you are oscillating. It's always symmetric. It's always the same type of fluctuation around the minimum. Whereas in here, no, it's not. Okay. Right. So what is the mass spectrum then? What happens to the masses of these particles? So let's study now the mass spectrum. Right. So what we to study the mass spectrum, what we do, of course, we want to finding the quadratic terms in the minimum. But the first thing is we really need to know that we are in the minimum. Mathematically, this is what we do. We are in an extremum, so we have the stationarity condition that we have just checked with the first derivative. And now let's check if this is a minimum, it's a maximum, or a saddle point. And we do that looking into the Hessian matrix. And if you remember, if the Hessian matrix has two negative eigenvalues, it's a maximum. Because negative, you can have this analogy, negative because they want to fall down the hills of the potential. So going to negative direction. Positive eigenvalues, both directions want to go going up the potential. So it's a minimum. One positive, one negative, it's a saddle point. So it's one direction goes down, the other direction wants to go up. So for this, we evaluate this just stands for the derivative, the second derivative of the potential with respect to the fields, which we take as this d2v d phi I d phi j d2v, sorry, this would be d phi I squared here, d phi I squared here, this phi I d phi j d2v d phi j d phi I, and sorry, I'm just, this is 1 and 2, 1 1 2 2 1 if I so okay, right? So, and this is what we define as the mass matrix with the squared. So we always keep squares in this, in the scalar mass matrices. This is ij, so this is defined as the mass matrix, and in our particular case of this potential, what we get is m squared is equal to the following: mu squared plus 3/4 lambda phi 1 squared plus 1/4 lambda phi 2 squared 1/2. Sorry? Those are lambdas, yes, yes. Yeah, my lambdas are a little bit curly, but yes, these are lambdas, yes. And here again, 1/2 lambda phi 1 phi 2 and mu squared plus 1/4 lambda phi 1 squared. Well, you can confirm this later on. And there might have some exercise along these lines as well in the next example sheet. So now this is just I'm saying this is a mass matrix, but this is not yet applied. This is not yet in the minimum. This is the generic second derivative, the generic Hessian matrix of the potential. Now we need to apply the minimization conditions. That is, we need to, or the extreme conditions. So what we have to do is let's apply this for potential A. So for case A, where we had lambda and mu squared are both positive, so it was this potential. Let me go back, this potential here. So we are going to see what is the mass spectrum in this case. So we want to be here. We want to be here in the minimum. Right. So what we do is in the minimum, so m squared at phi 1, this is, I'm writing it different. Oh, sorry, I just changed the notation of the phi's. Phi 1 equal to phi 2 equal to 0. Here, this phi should be, so phi I should be phi I. Just I just wrote this as in the notes, not as with the notation that I've been using here. Right, so m squared in the minimum, you apply this, and it's trivial to see. You look into this mass matrix, and you see the only surviving piece is the mu squareds. So both mu squareds are the only surviving part. So it gets a diagonal mass, 0, 0, mu squared, with both mu's positive. So in this case, since both mu's are positive, we conclude that we have 2 degrees of freedom So the mass of phi1, so this means that we have m phi1 squared equal to m phi2 squared equal to mu squared. And this is positive. So we are in the minimum. And this is not surprising because we don't break any symmetry. So we just get the mass of the. So this was a Marcus question in the beginning. But if mu is negative, don't you have tachyons and so imaginary masses and so on? So this was a Marcus question. So here you clearly see that we are face to face with the Klein-Gordon complex field. So both fields are the same. So you can simply say that you have one field, one complex field, which is m phi squared. I wrote in a different way. M phi squared equals to mu squared. So this is the mass of the field itself, and it's reflected in the Lagrangian that we wrote in the beginning. On the contrary, if what happens if we are coming to case C? Let's see what happens here in case C. But in this minimum, let's not be in this maximum here. In this minimum, what happens? So case C. For case C, and here I will use again. I want to use just the origin again. So phi1 equal to phi2 equal to, just to compare with above one. So we get the same mass matrix. So, but we have now, so lambda is positive, I guess. No, lambda is negative and mu is positive. So this does not lead to anything. It's exactly the same thing. Case C, I wanted to do case D. So in case C is exactly the same thing, just it's not completely stable because the potential then goes negative for large field values. But I meant case D here, case D. Lambda is positive and no, negative, and also mu squared is also negative. So what happens there? So we are now sitting here. We are now sitting here in this minimum here. Our mass matrix will simply be the following. This, but I will now put here modulus and a minus. So we have our m phi1 squared equal to m phi2 squared, both equal to minus modulus mu squared, sorry, modulus of mu squared, which is negative. So this is clearly when you see negative squared scalar masses, you say we are not in the minimum. The theory is not exactly. The theory is not. I'm not in a minimum. There is no stability in this minimum. I'm in a maximum in this case. So this is to discard immediately. Now let's go to the most interesting case, which is case B. So case B. Case B. And here we are, recall that we have lambda positive, mu squared negative, and we are not going to study in the origin because in the origin it's just a maximum. We would have like negative, the same masses in case D in the origin, but we are going to the other solution. So the other possibility where we have phi1 squared plus phi2 squared which is equal to v squared, and this is positive. And we have our condition where mu squared is equal to minus 1 over 4 lambda phi 1 squared plus phi 2 squared. Right. So we have, going to our mass matrix, m squared at the minimum. So what we do is, with mu squared equal to minus 1 over 4 lambda, and I will write here. For now, I can still write. Minus 1 half lambda. Okay, there is. I need to correct something then back at home. But yeah, but still, we have we apply the minimum. Let's put here lambda v squared. Let's use this, and now we replace in the mass matrix. We replace mu. What we do is we come to this mass matrix here, and we replace mu here and here by that value. And when you do that, what we get is the following. We get this 1/2 lambda. Let me do something. Let me still use here phi 1 squared plus phi 2 squared, because I want to write in terms of field values still. Lambda phi 1 squared 1/2 lambda phi 1 phi 2 1/2 lambda phi 1 phi 2. You see, we have eliminated mu from our mass matrix. This is the condition to tell you that we are in the minimum. So we remove mu from the theory. Well, we trade it for something else, which is going to be this v, or the sum of phi 1 squared plus phi 2 squared. But this is not yet, we still don't have a physical interpretation of this, because this is not diagonal. So we don't know yet what are the masses. So to obtain the physical spectrum, we need to diagonalize m squared. To obtain the physical mass spectrum, we need to, and this is like step number 2, we need to diagonalize m squared. And to do that, so I'm not going to be here calculating the eigenvalues and eigenvectors explicitly. That's something with Mathematica, or you do it immediately. But what we get is that our m squared goes to something that I call, let's call it m, small m. And this is going to be equal to, after diagonalizing, the mass matrix will look like 1/2 lambda phi 1 squared plus phi 2 squared 0 0 0. We get this too. So okay, and we can write it simply as, now I will write with v 1/2 lambda v squared 0 0 0. So we obtain a new, so m, it's no longer phi 1. In fact, here they are going to be identical, but I'm going to be phi tilde, because the eigenvectors are a combination of the and in fact, yeah, there will be a combination. The eigenvectors are going to be a combination of the gauge basis. So this is this is in the mass basis. So let me just write, and I will tell you. 1 half lambda v squared, and m, the second one, m phi 2, oops, tilde squared equal to 0, which is associated to this 0 and this one to that one. What happens is that you diagonalize, you calculate the eigenvectors, and the eigenvectors are a combination of the previous basis eigenvectors. So that's just how you diagonalize something. So M, big M, is written in what we typically denote as in the gauge basis. So gauge or flavor basis. So gauge because it's the basis where we define the gauge properties, the gauge symmetries. Gauge or original basis. And M is written in the mass or physical basis. And phi 1 and phi 2 are eigenvectors of the gauge basis, whereas phi 1 tilde and phi 2 tilde are eigenvectors of the mass or physical basis. So basically, it's the mass basis that define you the physical interactions, because it's what you can measure are interactions in a basis where that diagonalize the mass form, basically. So all other interactions that emerge from here, and we will also see that, of course, they result from a rotation of the original basis to the mass basis. The ones that we diagonalize are the quadratic ones, and then all the other interactions should be rotated to the same basis. We need to identify the eigenvectors and plug in the eigenvectors in the original Lagrangian to see what are the physical interactions that we can measure. So what happens is that you see here that you no longer have the same two particles with the same mass. So there is already here a breakdown of symmetry in terms of when you start identifying the masses. Two different masses. So far, when we were in the minimum, in the 0, 0, so which we can call the symmetric minimum, the masses there were always two equal masses. So there was clearly a symmetry, not only those geometrical discussion that we had that doing fluctuations, it's the same in any direction, that reflects in the same mass for all field directions. Here you're clearly seeing that depending on the field direction that you are taking into account, you have a different mass. And in fact, this phi 1 tilde is going to be the radial direction. It's going to be aligned with the radial fluctuations, and phi 2 is going to be aligned with the angular direction. And it doesn't cost energy in the angular direction because there is no walls of the potential to climb, so it's massless.
I have a question about how to interpret something like this, where this might be one of those cases where the fact that you can visualize it makes it worse. But I'm trying just to interpret this idea of the resistance that the field has to moving out of the potential, or lack of resistance. I'm just trying to figure out how does this translate? Is there an intuitive way? It translates into mass because the mass basis has that mass, and in the math, that's just how it works out. But I have some trouble figuring out. So, for example, in the radial direction or the angular direction, if you have a field with that configuration, that particle, it could be any possible choice, yes?
Yes.
So yes. It's, and in fact, without you know, depending on initial conditions, it could be oscillating between all possible modes. Yes.
All possible modes. What are possible
But,
modes? Here we're
okay,
talking
in the
about
sense, in all possible particles that are compatible with the minimum, right? So in
we have
theory,
two
phi 1 is
particles over
radial,
here.
so it's always the same, but phi 2 could be changing its properties, or however you would define the property of a particle in that
Phi 2 is
value.
an angle.
Right, yeah. So, but phi 2, exactly.
You
When
can
we
think
say
of
that
phi
it's
2
not
as an angle.
symmetric, yeah, but if it's not symmetric, then that means, you know, phi 2 equals 0 is different from phi 2 equals pi, yes?
No, but it's phi 2. This is the mass. I'm not saying that phi 2 is 0 or it's pi.
Yeah.
That's like,
Yeah, but the point is that I can go from phi 2 at 0 and phi
Yes.
2 at pi
yes,
without costing me energy at all.
exactly.
So there's no reason the system will prefer one over the other. And depending
Exactly.
on,
This in fact becomes non-physical in a gauge theory,
okay,
and can be removed because of that.
okay,
But the other one, no. The other one is a different story. The other one, it does have radial oscillations do cost this energy, let's say, and that's why you have this mass, essentially. And this is
yeah,
all like this can be seen clearly when we start writing things in terms of quantum fluctuations around the minimum, which is kind of the next step that I will introduce,
yeah, all right.
essentially. But let's see, maybe goes along a little bit along the lines of the discussion introduced by you right now. So we can uh, without so we can recast phi 1. So recast or let's consider quantum fluctuations. Consider quantum fluctuations about the classical minimum or the minimum V. So to do that, so V is real. So we say that our phi 1 can indeed be expanded in terms of, so there is a V, which is the classical value or the VEV, plus some H, which is, this is, so this is a dependent of X. So this is a field that depends on the space-time coordinates, Hx. And we have our phi 2. So there is no VEV in this direction. So we simply write it as like Gx, which means that we can rewrite our field phi in terms of these quantum fluctuations. So H and GH quantum fluctuations. One is the radial. This is radial. This is angular. But we can write this in terms of 1 over square root 2 V plus Hx plus Gx. And of course, this is phi x. Right. And now we can use this, because now what am I doing now? I'm just saying that there is like a quantum fluctuation and an angular one. And the quantum fluctuation is around the minimum V. So it deviates from V if I consider radial quantum fluctuations. So do you understand this picture? So it's the one that goes up and down the hill. But the angular, no, it does not deviate from V. So we just keep it as this G. And now we can plug this phi into the potential. So using um, mu squared equal to 1 over 4 lambda v squared for mu squared negative, and replacing phi x in v phi star phi, we get, so we can recast our potential as v h g. So I'm dropping, I will drop the x now. This was just to identify what are the quantum fluctuations and the classical field configuration. And we get at the end 1 over 16 lambda g to the power of 4 plus 1 over 8 lambda g squared h squared plus 1 over 16 lambda h to the power of 4 plus 1 over 4. And we'll read a lot of things from here. Lambda v h g squared plus, further below, oops, what am I doing? Plus, so lambda hg squared, 1 over 16, okay, 1 over 4 lambda v h to the power of 3 plus 1 over 4, there's only two more, this one and another one, lambda v squared h squared minus 1 over 16 lambda v to the 4. So let me just count 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Okay. So the very first thing that we observe is this green term here. So we have concluded above, we have calculated from the minimization that the mass is 1/2 lambda v squared. So here we have, so this is equal to 1/2 m h squared, right? So this is the mass term. Now, because this is a quadratic term in H, so let's look for quadratic terms on G, involving only G, which doesn't exist. So this is a power of 4 term. This is a power 2, but there is an H here, so this is not a mass term. This is power 4 of H on it. This is power of 2, but there is an H here. So this is not a mass term. This is not, and of course, this is a vacuum energy term. So this is nothing. So we clearly see that we don't have also a mass term for G here. So this respects what we have seen by diagonalizing the mass matrix. So we are doing the same thing in two different ways. One was diagonalizing, the other one was only identifying the minimization conditions and expanding the Lagrangian in terms of quantum fluctuations around that minimum. And we are reaching the same conclusions. The advantage of this method here, which is not always used, but the advantage of this is that we also identify other properties of the theory. Another one is that you see that G always comes in powers, in squared powers. So the interaction terms involving G are these ones that I will identify. So we have this, we have this one, we have this one here, we have this one here, and that's it. So they all come, they always come in a squared power. So there is an invariance. There is an invariance of G going to minus G. So the potential remains the same. So here, this is a Z2 symmetry. It's a discrete symmetry. There is not a Noether charge associated to this Z2 symmetry, because the infinitesimal, so the transformation property when you do the infinitesimal transformation is 0, so it kills off immediately the currents and so on. Um, but what we see here, what you clearly see here, is that when you in the minimum of your theory, you have a U1 theory global, it was a global, that is broken down to a Z2 symmetry. This is how you do this, how you identify the symmetries. But you also have other interesting things which you can find self-interactions
Sorry,
here.
before
Yes.
I just wanted to ask, if we had considered a complex field where, you know, instead of phi1, phi2, we had phi1 and I phi2, something like that.
Yeah, but
Yeah.
this is exactly what we are doing.
Okay, but would it still be Z? Because I'm thinking if G is allowed to be complex.
G is real.
Okay, so but there isn't any way that we could set up the problem so that we would have a complex
No,
analog to it.
because G is clearly
Okay,
real. Another
right.
thing is if you have a Z2 symmetry on phi itself, on the big phi, on the complex phi. That's a different story. And we are going to see that next lecture. In fact, we're
Okay.
going to study that. I want to cover all those possibilities. But
It
in
doesn't
this
make
case,
sense.
it's real.
If G was allowed to be complex, then you wouldn't have a broken symmetry, right?
But yeah,
Because
exactly.
it would be U1.
G is it's the imaginary part of the field, but the imaginary part is a real.
Yeah,
Is a real component. So you are expanding a complex field. There is one complex field which has 2 real degrees of freedom, and we are expanding the potential and the Lagrangian by extension in terms of their real components. And this is exactly what we are doing to.
Maybe quaternions have a SO3.
Sorry.
Quaternions.
But
they have SO3 symmetry, if I'm not mistaken.
I
Or
don't know.
maybe
But what
it's
is that?
something like that. Because then we could have something
SO3, yeah,
with the
because
complex.
the translations. Quaternions, they have like.
I think it's SO3 cross something.
Yes. I don't know which one, but yeah, it's something like that. It's
and then
not,
maybe you could have something that breaks it down to U1, but that would still be broken. Yeah.
Yeah, but here it's start already with U1, and
Yeah.
it's,
Okay.
this is
yeah.
the simplest scenario that you can think of, essentially, an abelian global mode. Of course, so what you clearly identify here, and is that, and this is the last thing, just to. So you identify, as I said, mh squared equal to 1/2 lambda v squared, and mg, I will just write squared because of consistency, equal to 0. And this is a Goldstone boson. This G is the so-called Goldstone boson, which today is introduced in this manner. Goldstone boson. And here, this is a Higgs-like boson. Higgs-like boson. Note that the Higgs boson is not the big phi. The Higgs boson in this case is the H. And it has this mass. And the other partner in the original complex representation is a Goldstone. In the next lecture, we'll start with the Goldson Theorem and the proof of Goldson Theorem, where this is going to be, it's quite elegant, actually. It's something that I really, it's clear that these massless particles do have to emerge when you have a continuous symmetry, and there is a spontaneous breaking of such a continuous symmetry. But also, here in this potential, look that we have interaction. So this is a cubic interaction of 3 Higgs, so that you can write in this with this type of Feynman diagram. This is a mass, just here H. And if you measure this cubic interaction in colliders, for example, you know that this is going to be proportional to this lambda and v, essentially. So you can measure these quantities by measuring this interaction. So, for example, if you can identify a process that has this cubic vertex, in experiments, you can extract its value and put constraints on the values of lambda and v. Of course, in the standard model, this is already quite well constrained. It's not yet measured this, of course, but there are other measurements. The mass itself puts constraints on lambda and v. We measured this, the mass. And also the masses of the gauge bosons, which are proportional to v, not to lambda, but to v. We will see that also very soon. There's also this lambda to the fourth. This is a quartic interaction, and this is like, as we have seen before, like this type of interaction. I'm not talking about the Goldstones ones here because these Goldstones, these are phases, and they can be phased away. In fact, we will see that in the next lecture. So in the next lecture, we're going to talk about the Goldstone Theorem and also how to phase away this. What is a better representation to remove these phases? Also talking about explicit symmetry breaking and comparing to spontaneous. This was a spontaneous breaking, what we have been doing now. We didn't force anything, but we generated a mass for a particle and another one becoming massless. There's a just by having this minimum, you spontaneously break the symmetry in that minimum of the potential. The properties of the potential are such that the Yuan symmetry of the full potential does not hold in the minimum. That's what we meant by spontaneous symmetry breaking, which is not the same as explicit. And the shape of the potential gets a bit funnier when you have explicit breaking. Yeah, and we are also going to try to see how gauge bosons get mass in an abelian way. Okay, so Thursday is still SM1 course. Let's see what we can do, if we can get at least almost to the end. And so guys, see you all on Thursday. And also don't forget to send your exercises.
Yeah, so the deadline is today.
Yeah, you can send
I was going to ask if you could just do tomorrow. I just
okay.
They're pretty much done. It's just a matter of what I would have to work after dinner.
Okay, it's fine. If you can send it tomorrow, you can send it tomorrow. It's fine. It's fine by me. If someone else now, it means that everyone else that wants to send tomorrow can also send tomorrow. That's just the consequence.
Yeah.
We should send to your email then.
Yeah, you send to my email. Yes, when I get all of them, I will check them.
Okay, thanks. Just one more thing. I think lecture 5 is not available. I think there's a broken link.
Yeah, the notes of the lecture, right?
Yes, the notes. Yeah.
Okay, I will try to fix that. But thank you for telling me that. I didn't know that.
Okay, thanks.
Okay, guys. I will wait for your exercises, and we see each other Thursday again.
Yeah, hopefully.
Okay, thanks. Bye-bye.
Okay, bye-bye.
Bye.
Thank you. Bye.
Bye, thank you.